Good afternoon and welcome to MAE 209, Lecture 25, Confidence Intervals. My name is Richard Kohar, and I'll answer a couple of questions that I've already seen in the chat. The quiz will be in person. We're going to have an in-person quiz slash lecture on Thursday. So we'll have a quiz on Thursday. It'll be in person. It'll be 20 minutes. And you can have a non-programmable scientific calculator. One without graphing. So don't show up with a TI 83 or something else like that of that similar nature. And yes, it will be in person. Okay. So I think I answered all those questions that are at the beginning of there. I think I posted also which sections are on Moodle. I think it's 5.1, 5.2, 6.1, 6.2, and then 7.1. And this is what in the textbook we're covering is 7.1. Okay, so the basic concepts and principles of confidence intervals are mostly easily introduced by focusing on a simple situation. So we're going to suppose that we have a parameter of interest. So that's something that we want, is a population mean. So population, let's say expected value. Oh. We'll call that mu. And we'll also make the other assumptions that the population is normally distributed. And the second one is that we know the variance or the standard deviation. Okay, so we know that. So it's very common and it's a very realistic assumption that a population distribution is normally distributed. So let's say, for instance, here's like an example. So let's say that we have industrial engineers and they're working in the field of ergonomics, and that's concerned about designing a workspace that doesn't cause RSI, repetitive stress injuries, to workers. So for instance, like designing a workstation or designing some sort of furniture so that it supports movement. So let's say that, we're going to say engineers, and they're designing some sort of like a wrist support for keyboards. And they want to know what the height of the support should be. So they're designing it and want to know the height. For the support. Okay. And so, again, not everyone is going to be the same, right? Everyone is going to be slightly different, but what they would like is to have some sort of average. So what they went out and they did a sample. So they did a sample. And they did, say, 31 typists. And they measured their height of the wrist support. Okay. So when they did that, when they calculated the average, the X bar, they found that it was 80 centimeters. Okay, so then they assumed so what they did was they assumed that it was normally distributed. With a standard deviation of 2 centimeters. So this is kind of our running example problem. So they want us to construct. So construct a confidence interval for the expected value. What we want is we want the expected value for the population. So for mu, which is the population. So the population expected value. So notice what we're doing is we're trying to go from a sample to inferring what the entire population expected value should be. So construct a confidence interval for mu, which is, in this case, that would be the true average. Preferred height for the population of all typists. Okay, so that's what we're going to do. Is we're going to construct an interval around mu. So again, think of it just like an interval. When we have something like, we have, say, mu, and we would like to have something that kind of bounds it. So again, what we're going to do is we're going to start off with what I'm going to do is I'm going to pause this example. We'll return to it. So we're going to construct constructing an interval. So constructing a 95% confidence interval. And they'll abbreviate it sometimes as CI. Okay, so we're going to base this around the normal distribution, but on top of that, we're also going to make this based on the standard normal. So we're going to start off with the standard normal, which is, we're going to use Z. We will use x bar minus mu all over sigma. And this is where we also have to take into account the sample size. So again, the sample size will have sample size as n. We have the expected value. Oh, well. We have the sample mean. And we have kind of the standard deviation. Okay, so that's kind of the standard normal that we'll be working with. And what we would like is something like we'd like to have a normal distribution, and that we would have some sort of like mu is within this range, and we would like to have it under 95% of this area. So this is kind of what we would like. So to do that, what I need is that my probability has to be between some sort of number A, and we'll go less than Z, less than B, and that this has to equal, we want 95% of the area. So what number gives us this A and the B? Well, what I can do is set A equals to minus 1.96 and set B equal to positive 1.96. So when I do that, just so you can see it, if I pull out my standard normal table, so I have 1.96. 1.96 is 0.975. And for the negative, should be symmetric, so minus 9.6 is 0.025. And when I subtract that, then I get 0.95. Okay. So That's what I would like. So therefore, what I want is minus 1.96. I'm going to bound that variable z. Okay, and then I'm going to replace my z with our transformation. So that's what I have so far. What I would like, though, is to express this inside, this inequality, just with the inside term here, just with mu. That's what I would like. So let's just take a highlighter. What I would like is this inside part right here. We'll just work with a little bit of this. So I would like the middle term to be mu. So what I get is minus 1.96. So I'm just kind of rewriting it. And then I'll multiply through by sigma over square root of n. So if I multiply by everything by sigma over square root of n, sigma over square root of n, and over here, sigma over square root of n. So what that happens is that this will cancel, and I'm left with that so far. Then what I would like to do is I'm going to subtract the x bar. So doing that, what I can do then is okay, then this will cancel out so that I'm left with minus mu. And I'm just going to bring this out in front. I'll have the minus x plus 1.96 sigma over square root of n plus okay so far. Then when I multiply by minus 1 to get rid of this, I can eliminate all these minuses, but again, when I multiply by negative 1, the signs will flip. I gotta be careful. I have a minus here. So just gotta make sure. Yes, somebody has noticed that already. Thank you, Eric. Yep. And so this should be plus. And then, well, what I'm going to do is I'm just going to just kind of flip it, right? I'm going to just kind of write it so that, because I have just to write it as it's kind of going it this way, and I'll write it the other way. I kind of want it to go in this direction. So I'll write x bar minus 1.96 sigma over the square root of n is less than mu is less than, I have x bar plus 1.96 sigma over square root of n. Okay, so that's what we want, and what I'll do is I'll put this back up into here, which was the probability of it being within that interval. So therefore, the probability okay. So you can now think of this as a random interval, where the left point over here is x bar minus 1.96 sigma over square root of n, and the right point is x bar plus 1.96 sigma over square root of n. So you can think of it as a notation for intervals as so in random interval notation, what you can think of it as is x bar minus 1.96 sigma over square root of n, comma, and then the plus. So they're very similar, except for right here. That's what it should be. So that's just the difference. Okay. I'm not sure if you mentioned this, but are we allowed to bring our own formula sheet for the quiz? No, you're not allowed to bring a formula sheet for the quiz. Okay, so you can think of that interval as random because you have two endpoints and they involve a random interval, which is mu. Now, you might start to think, well, what you can say is that what this says is that the probability is 0.95 that the random interval includes or covers the true value of mu. So before any experiment's performed, or if you collected any data, it's quite likely that mu will be inside of that interval. Okay. So just as a little diagram, we'll have x bar, and here's our interval here. So we'll have x bar minus our 1.96. And again, we calculated that 1.96 from our z table. So it doesn't just come out of nowhere. It's not a random number that it's a number we've picked for that specific purpose. And what that would say is that, here's kind of our interval. So that's our random interval centered at x bar. So let's just kind of write that out as a definition. So if you have a random sample, so you have x1, x2, the way to xn. So those are little ones. These are realizations. Then you would have a sample mean. Then the 95% confidence interval for mu is so we can express it either way, but we can have little x bar minus 1.96 Okay. And what they generally call the left-hand side is the lower bound. Or the lower limit. And over here, there's the upper bound. And that's our confidence interval. Now, let's go back to that question that we had, which was, we had the engineers. So we had engineers designing that wrist support for keyboards. We had a sample of 31 typists. We had X bar, our sample mean is 80 centimeters, and we're going to assume that it's normally distributed with a standard deviation of 2 centimeters. So then we can construct a confidence interval for mu. So that's what we'll do now. So I'll just write, going back to our first example. So going back to example 1. So let's just make sure I label that as example 1. We can construct our CI. So notice how we were saying construct a confidence interval. Well, you need to specify what level of confidence you would like. So we're going to specify that it's a 95% confidence interval. So for the true average preferred height, okay, so I'll use this definition here. I need to use my x bar. So my x bar in this case is 80. So I have x bar is 80. So it's 80 minus 1.96 with the standard deviation of 2. And we said that there was a sample of 31. So that's the square root of 31. You'll have 80 plus. So here's our upper bound. So are we always looking for a 95% confidence interval? Now that's a good question. Not all the time. It depends on what the design or what the tolerances or whatever the specs that the engineers have to design to. So for instance, it might not be good enough that's 95% confidence interval is good enough for, say, for wing design or for aerospace design, right? Because I know a lot of people in this group are for aerospace design or for flight, and they may want a higher confidence interval. So it's not always that we need 95. We could say have 99 or 90%, and we will show how to get that. So we have a confidence interval, and what I have to do is calculate that. So I pull out a calculator. So I'll have 80, and over here I'll have 1.96 times 2 divided by the square root of 31. So if I take 80 and subtract that, I get 79.2, let's say 3. And over here, oops. So I want that answer plus 80. And I'll have, nope, that's not right. 80 plus point. There we go. So we are always looking for, will that change the 1.96 figure? That's right. That's right. Okay. So that is, we can be highly confident that at 95% confidence level that mu is 79.3 and 80.7. That interval is relatively narrow, and it indicates that mu has been rather precisely estimated. Now, we got to be very careful on the interpretation of it. You know, it's incorrect to think that the probability that its mu is between it's kind of incorrect to think about that, because that's not the way that we've been interpreting it. We think of that 95% confidence means on the long term. Because again, we're basing this 80, or this 80 was found by X bar, which is based on the sample mean. So again, we could have different data that comes up, and that would change our interval here. So what this actually means then, that on the long term, what it means that if you perform this experiment many times, in the long run, that confidence interval of the computed CIs, again, because they're based on experimental data, will contain mu. And that's why, because the computed CIs contain the samples. So what this is trying to say is that if you repeated this experiment over and over again, and you calculated these CIs, 95% of those confidence intervals will contain mu. Yes. And although that this may seem unsatisfactory, the root of the difficulty lies with our interpretation of probability, which means that it has to apply to a long sequence of replications of an experiment rather than just a single replication. Okay. So, as Curtis has pointed out, we can calculate other confidence intervals. So, here's our definition. If you have 100 and you'll have a 1 minus alpha %, So again, the alpha would kind of is what we use for our confidence interval. For the mean of a population. When sigma is known. So that's given by, we have x bar minus, and we have our z value of alpha over 2, right? Because we need it to be symmetric. So we need some area over here as well as the area for the upper bound times sigma over square root of n. And we'll have this less than mu less than x bar plus z alpha over 2. So we have the plus, and over here is the minus. So that's our interval. You can also express this as words, so you could have that or equivalently. You can have x bar plus or minus z alpha over 2 times sigma over square root of n. And what you can think of that as is the point estimate of mu here. Then over here is the z value. And then here is what we referred to as the standard error. Okay, so let's finish off then with the example. So let's use that typing example. And instead of 95%, we'll use a 90% confidence interval. So what that means is that alpha is equal to 0.1 and that z value will have our we need to have 90%. So instead of 90, what we need, instead of the 1.96, what we need is 1.645. Okay, and that's calculated similarly how we got the same number for 95%. Then what we do is we go back and we use our data that we had. So we can use this, and again, x bar is 80. So So we have 80. We'll have plus or minus our z value, which is 1.645 times the standard deviation, which is 2, over the square root of 31. So same thing, 1.645 times 2 divided by the square root of 31 gives us 0.59. So you can think of that as $79.4 and 80.59. So that's our 90%. And if you notice, this is what we got for the 95% confidence interval. We had 79.3 and 80.7. And over here, we have 79.4 and 80.5. And then it's actually smaller. So the 90% confidence interval is smaller than the 95% confidence interval. So how we get the 1.645? It's very similar to how we do it on this one right here. So instead of setting it to 0.95, you would send it to 0.9. Then you will have to go and look for the values on your standard normal table. So if I set this, so let's say I set A. So in this case, I need to set it to 1.645. So if I look at my table, oops. That would be minus here. Then I looked up that value, which is 1.645. So we have 0.949. So you would take kind of like this average here. So you would get something like 0.95. So 0.95 minus, and same thing over here. If I look over on the negative side, negative 645. So I would say 0.5. That gives me 90. Okay? So that's how we were calculating it. So what I wanted to say was, why settle for a confidence interval that's 95% when you could have a level of 99%? It's simply because the price paid for a higher confidence level is a wider interval. Okay. So the higher the confidence, say confidence percentage, say that, leads to a wider confidence interval. Okay, so that's all that we have for today. The practice questions are posted on Moodle. If you have any further questions, again, feel free to send me an email at my RMC email address. If there's no further questions, enjoy the rest of your afternoon. Okay, take care everyone and enjoy the rest of the afternoon.